Okay. Okay. So we all understand that the e is a number, it's a base. Okay, so the actual function h of x is actually this guy right here, that x to the natural log of x. So if I take the derivative of this h prime, I have e x natural log of x, that stays the same. But now I have to take the derivative of the exponent. So if I take the derivative of the exponent, I leave x alone and take the derivative of natural log of x. Now, the natural log of x is 1 divided by x, plus the natural log of x stays the same, and then I take the derivative of x, and that is just 1. So here I'm going to simplify. This will just become 1 right here, obviously, and then I have my derivative is equal to e to the x when I clean it up a little bit, times 1 plus the natural log of x. Now remember, the natural log of x, when we look at the graph, it hits 1 and it's going to be 0. Okay, that's like the general shape of it. Okay, now this is obviously equal to f of x, so I'll just do that there. So what we're graphing is the rate of change of it. So the rate of change of this says that it looks like 1 over x. So we all know 1 over x looks like, if you kind of remember that, 1 over x, I believe, looks like this, and then looks like that. So, well, although the derivative is a little bit unorthodox compared to like doing a power rule of a polynomial, that's what this looks like. So this actually describes the behavior of natural log of x. Notice that it never hits 0, right? The same thing with natural log of x. If you ever graph it, it just comes down but never hits 0. So this is negative right here for all the values here and 1. Then once it hits 1, okay, then it's moving up, it's increasing. So now I'm looking like it's moving toward this direction, but never hitting that axis there. So in this situation, the natural log of x, the derivative of that will always be 1 over x times the derivative of the function below. So here, this is what I have as my final product, or I should say not product, but result. So it'd be 1 plus natural log of x times e to the x natural log of x. So that's what I have to do there. Notice what rule did I use here? I used a product rule because I have two functions, x and I have natural log of x. Okay. So that's the first step. I mean, obviously that's the first question you asked me there. Hopefully that makes some sense. But then you look yourself, okay, but what about 5 and 6, right? 5 and 6 look nothing like natural log of x. I have one function that says natural log of, I believe it says natural log of e to 2x plus 1. So let's take a look at that one. Can I erase this up here? Okay. So I'm going to go ahead and erase that. If there's nobody else complaining about that, I'll erase that. Okay, so the next one here, j of x, I want to take the derivative of this function. So j prime of x. Now remember, again, if f of x is equal to the natural log of x, where x is, inside here, any function it can be, then f prime of x is equal to 1 over x times the derivative of x is 1, right? Taking the derivative of that. So in this case, the derivative of this function is 1 over e to the 2x plus 1, and then we're going to multiply it by the derivative of that inside function. So what would be the derivative of e to the 2x plus 1? So obviously the derivative of 1 is 0, but e to the 2x will be 2 times e to the 2x. So therefore, j prime of x equals to 2 times e to the 2x over e to the 2x plus 1. Now, before I move on here, are you starting to get kind of like that pattern of what I'm doing with the natural log? Notice how, so you notice how I'm going from this function, when I take the derivative of it, I'm writing it as 1 over, and then times the derivative of that denominator.
Yep.
So the next one is going to be a lot easier because this is just 3 minus 2x, right? So I'll leave it for you to sort of like fill that one out. You're going to write it as 1 over, what on the line here or over here, and times the derivative of that.
Okay, thank you.
Yeah, no problem. All right, I'm going to go ahead and clear this. Or not yet. Anybody else want to write down what I just wrote down? Okay, I'm going to go ahead and clear it. Okay, so I'm going to stop recording for a moment so you guys can, I don't want to have so much like dead air time as you record. So if you got the first equation, a to the e ax, then the second equation was just taking the derivative of this guy again. So right now, if you got both of these, you already have a point. And then if you evaluated it, there's the other 2 points. So I think how I had it set up, it was like an 8-point FRQ, but I'm gonna make it 5 because I think part B is the big part where you have H prime. All you have to do was use the values that they gave you for, I believe, f of 0, f prime of 0, and f double prime of 0. So this guy is going to be 3. This one's going to be -4. Obviously, if I put 0 in the exponent here and here, I'm going to get 1 as my function evaluation. Let me see what we have here. Okay, the double prime means the second derivative. So if this is my first derivative function here, then I take the derivative one more time to get the second derivative. So I'm starting off now with this function. And I take the derivative of this again. So following the same steps, a is a coefficient, right? So I don't do anything with that. So a comes down here, right? This guy comes down right here. But now this function is derived one more time. So just like you did it the first time, the a pops down, right? And I still write e to the ax plus. Now, if I take the derivative of f prime of x, basically I'm taking another derivative of it again. So this is f double prime. This is to denote that this is the second derivative. So a times a is a squared. And that's the general form. Hold on a second here. Let's see what you guys have to say. Oh, at times it makes sense. Makes sense. Okay, got it. Right, exactly. So that's what I have. So again, it's getting you guys familiar with the fact that I don't always have an equation, okay, per se, always. It's still following, it's like understanding like I'm still following the same derivative rules, okay? So the way I've always described it to you in the beginning was h of x is equal, like say, for example, it was product rule. I always said h of x equals to g times f, some general function. And then I showed you what it looked like when I took the derivative of it using product rule. Then we started substituting it with like polynomial equations for our beginning, you know, examples. And then we got more complicated with like cosine functions and so forth, and exponent functions. Okay, for the evaluation, okay, that's a good question. So remember that this was supposed to be evaluated at 0 after you took the derivative, right? So if I take that and I plug it here and here, obviously we knew what these were going to be, right? Like these guys at 0 here, this was equal to -4, right? But if I plug this into here, e to the a times 0, then my whole exponent goes to what? 0, right? So it's a squared times e to the 0 power plus 3. So what's anything raised to the 0 power? It's going to be 1. So therefore, this is just going to leave me with a squared plus 3 as my answer for g double prime of 0. Does that make sense now? Okay. So with this being said, I'm going to go ahead and clear this part. We look at the second part. This is a part that I think a lot of people started to get this correctly, but they were still kind of like shaky about it because again, there's this k value right here that like, well, what's this k? You guys love to see numbers and forget that you're still going to treat this as it were a number, okay? It's called a constant. It's just a coefficient. So notice that the derivative of cosine kx is that negative sine kx here, right? But what you don't see sometimes when you were taught this in the beginning is that what you really have is a chain rule property that's happening with this. That's why it's cosine in parentheses x. That's like saying cosine was h, and this is saying h of g, for example, right? Or f of g. That's like going back to calculus, I mean pre-cal, like those fog functions. So if I have h of g, this is really saying h of g of x. So that's what I have here. Cosine is the h, kx is the g. So if I take the derivative of this function, I go to f prime. We all know that it was going to be negative sign, right, guys? We all know that part. The inside function was actually left alone because we took the derivative of the outside first, but then we have to take the derivative of the inside. So multiply by the inside function, which is, if I take the derivative of kx, I'm just going to get k because x is only to the 1 power. So if x is to the 1 power and you take the derivative of that, the 1 comes down, it's now x to the 0 power, and we all know that, we should know now, that x to the 0 power is 1. So 1 times its coefficient is the coefficient itself. And so what you really have here is negative k sine of kx. So we don't normally see that. You're like, well, how come, you know, before I used to tell you that what's the derivative of cosine, like negative sine of x. You knew that right away because, again, the coefficient in front of the x inside here was actually a 1. So when I took the derivative of that function, I get negative sine of x. What am I multiplying it by? When I take the derivative of the x inside, just 1. So 1 times this whole guy right here is just negative sine of x. So that's why they come up with this right here. So that's how they got this right here. I think most of you understood to take the product rule with this. Again, here we go with the function, right? Here's h of x, here's the function that they give to you in the beginning, and they give you another like general function expression. No equation, just a general function expression. If I find the first derivative, h prime, then f goes to f prime. That's it. Then I evaluate it at 0, and so I have the values here, right? All go for 0. So we do know one thing. This is going to go to 0. So I'm left with this guy at the very end. Okay? So let me record. So again, guys, the equation of tangent line is y equal to negative 4x plus 2. Well, they wrote it in slope-intercept because my x value is x equal to 0. So they just simplified it to this format. But if you notice in the rubric, it says equation of tangent line. It did not specifically say what format it wanted it in. So if you have it in point slope or slope-intercept, that's fine. Okay, so questions about 8, 9, 10, 11. Okay. Not too bad. All right, fine. Good. I like those kind of problems because, again, great representation of what's going to happen on the AP exam. They always give you a graph of f prime, and so you're either going to have to go back to f based on f prime or go forward to the next derivative, which is f double prime. So the graph of the first derivative, f prime of a polynomial function f of x is pictured to the right. Use the graph to answers 8 and 11. So what type of polynomial function is f of x? So given a reason for your answers. So here, do you notice that f prime crosses the x-axis at 3 spots, right? So at least here, here, and here. So that means f of x has humps at like 2 different spots, right? So if my f prime has 3 zeros, then most likely my type of function is going to be x to the 4th power, okay? Because I have, this function is cubic, right? So it's crossing it at 3 spots, 1, 2, 3. So the only way you can have 3 distinct zeros is if the function itself was a cubic function. Now, again, I'm talking about f prime, I'm not talking about f. So for you to get a cubic function, that means your function before that, f of x, had to be a quartic. Plus, you know, that bx to the 3rd plus blah, 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 blah. Does that make sense what I'm talking about, guys? Again, I'm looking at where does it cross the x-axis for f prime, because that's what it's stated for. So if I have 3 zeros for f prime, that means this was easily a cubic function. Like in this case, I believe this was probably a x plus 2 times x minus 1 times x minus 3. So let me denote this here. Here it is. Whoops, here it is. And here it is. So here are those zeros. That has to be cubic. So that means the function before that had to be quartic. And what are my reasons? I look at where it crosses the x-axis to find out exactly what type of function f prime of x is to give me what f would be. Any questions on that? Okay. So again, what am I using? I'm just using plain old Algebra 2 skills still to just visually look at it. Because remember how many times from Algebra 2 and pre-calc are like, how many times you have to find out the zeros of a function, the zeros of a function, set it equal to 0, factor, set it equal to 0. That's the reason why you do that. So the next part is, at what values of x does the graph of f of x have a horizontal tangent? Now this one should be not too brand new to you, okay, in terms of like how to solve this. Because remember, we talked about when f prime has to equal to what value to have a horizontal tangent? Zero. Thank you very much, Brandon. So if it equals 0, hey, guess what? Remember we talked about this in part A. I'm looking at where across the x-axis. So I'm kind of like doing two things. I'm doing two things right now. I'm actually answering 8 and 9 simultaneously. So I have my horizontal tangents at those values. X plus 2, x minus 1, x minus 3. Right? So that's going to be at what values are they? -2, 1, and 3. Then the next part talks about increasing and decreasing. And I don't think I feel like I need to go to this. Okay. Anyhow, let's not talk about chess. Let's talk about this. We have about 17 minutes. Okay. Can anyone tell me, review, how do I know f of x is increasing when I'm using the graph of f prime? Can anyone tell me? Okay, so we're looking at that all values of x-axis are positive, so increasing our positive values, right? Positive, positive, above the x-axis, very good. All three of you are telling me pretty much the same thing. Over the x-axis, I'd probably be a bit more direct about it, like above the x-axis, like the way Vivian said it, Sarah, which I think that's what you're meaning, like over, okay? So that means what values of x? So now, this is a continuous function, right? This is not discrete. I'm not going to label like -2, -1, 0, whatever. I actually have sort of an interval, right, of values. So can anyone tell me what my interval values are? What would be the first one? Or would be the first interval? Thank you very much, from -2 to 1. Now you're going to notice something about this. I'm not using brackets because that's including the point. I'm kind of using parentheses because that point is very peculiar, right? It's a zero tangent. So -2 and 1 sort of share between increasing and decreasing, right? And the other one, correct, is 3 to infinity, right? Right. So brackets were very, brackets probably be used for f of x, but not for like when you're describing something like moving and changing direction instantaneously at that point. So it's sort of sharing it. So it's like everything, because you think about it, right? At -2, that's 0. At 1, that's 0. At 3, that's 0 for f prime of x. So that's neither increasing or decreasing. So it has to be a point slightly after -2, right? Right here, slightly after it to be increasing. It has to be a point slightly before 1 to still be increasing. And it has to be a point slightly after 3 to be increasing, right? Exactly. Right, but it's for the f of x value. That's correct. It's for f of x. It's a definitive. It's like that's the reason why I need to kind of go back and talk about something about physics. It's position, velocity, acceleration, and then distance, speed, and obviously the absolute value of acceleration. When we're talking about the position of something, that's f of x. So we look at it and go, okay, yeah, I include that point. I'm actually 3 meters ahead of where I was before. I'm 3 meters in front, okay, or 3 miles away from my home in north, okay? So that's going to be a bracket. When we're talking about the velocity and things changing from positive to negative, I can't include the part where the velocity instantaneously equal to 0 for a single point because 0 is neither increasing or decreasing. So it's describing something physically different. So here, the next one, like you guys said, if I'm increasing, then all my points are positive above. Then decreasing has to be what? The inverse of that, right? Everything below the x-axis. So I should have, looking at this, 2 intervals of where I am decreasing. Can someone tell me where that's at? Negative infinity, correct? To negative 2. Correct. And then 1 to 3. Correct. That's it. Give a reason for your answers. You guys just said it, right? For part 10, you said because all the x values are above, since the graph of f prime of x is above the x-axis, those are positive f prime of x value. Therefore, it's increasing. The same thing for that. And you can simplify that too, okay? All right, so that's 8, 9, and 10. I'm going to go ahead and clear the drawings. And then I'm going to move up to something. So can we go number 5? Just thinking about that right now, actually. Number 5. Okay, approximation. What you have to do is you have to find the equation of the tangent line x equal to 1. So before you find, this is a 2-part question. So before you find the approximation, do what you normally would to take the derivative of f of x and then evaluate f prime of x at 1. So you see this as x squared times e to the x. Obviously, what derivative rule are we going to use to take a derivative of that function? And I'll write a little bit bigger. If f of x is given to us as x squared e to the x, what derivative, right, product, because this is, when you read it, you would actually say x squared times e to the x. So we're going to use product rule, right? So the first thing you got to do is you got to use product rule. I'm not going to go ahead and take the rid of this function because you already know what to do with this. It's actually a very easy function because we all know, now I've kind of said it a couple times, that the derivative of e to the x, plain old e to the x, is just itself, e to the x. So you have to find your equation of a line. You're going to get your slope after you evaluate f prime of x at 1, okay? And then all you need to do is fill in the y1 value, which you obviously will do when you plug it into this guy here, or this whole x squared e to the x function. Now, when they say approximate the value of 1.1, after you do that, after you find your equation of the line, then what I'm going to do, I'm going to evaluate this at 1.1. So whatever this is going to be, obviously it's going to be x minus 1. I'm going to put 1.1 into here after I have my y1 and m all figured out. Then I'll have my values here. So what they're asking you to do is turn the tangent line and use it as it was a secant line, okay? So if this was my curve right here, horrible curve, let me just do it one more time. If this is my curve right here, then it's asking me to take whatever this tangent line was and then all of a sudden kind of move it this way to go to the next point. So let's say this was my point right here that I found. That's the tangent line to the curve. So here, I'm going to take this guy, whoops, no, I shouldn't do that. Take this guy now and move it up just a little bit higher to the next point close to it, over here. So we're taking that same line that you found here, and approximating, which means sort of estimating what 1.1 would be, because it's very close to 1. Because you should have an equation that's exactly at x equal to 1, right? The line at 1. So at 1.1, it's just going to shift it slightly, okay? And so you're going to get an approximation that you're talking about. Okay. So I'm going to go ahead and clear this. So to kind of close off what we're doing for today, some of them are like in equation of a normal line. Remember, notice you have to use dy dx equals to 2. dy dx is the same thing as saying y prime, okay? Remember this, find each of the indicated limits below. You look at this and like, oh God, limit expressions. What does this really mean? Okay, here's the thing. Remember I told you we need to go back and take a look at what is the limit definition of derivatives. And so remember that this part, the x plus h, all these x plus h's, okay, here, is really telling me the derivative, this is really telling me this is f of x plus h. The original function is the one next to it where it says minus. So we're really taking a derivative of these guys. Here's my derivative. I'm taking derivative of this function. I'm taking derivative of this function. Don't include the negative sign because remember that's not part of it. Okay, take derivative of that function. Because remember that the original limit process, as h approaches it, I was generally speaking, it's like Michael J. Fox is like writing, huh? That was what was defined for you in the very beginning about a derivative. So we haven't really spent so much time with it because we kind of just moved on from it and just found easier ways to get a derivative. But we still have to go back and go like, oh, I recognize this. Because sometimes on the test, easily, like a couple problems on the test will just be like, look like this. And you're like, what the heck is all this? This is not a derivative. But then it is. It's just the limit process of it. So take a derivative of natural log of x, take a derivative of sine pi over 2, take a derivative of cosine pi over 4, and then take the derivative of the cube root of 2x minus 3, the way you normally would. Just kind of give you a hint. You look at C and D, notice that they're not taking, it doesn't say x inside at all. Okay, or like the way it says natural log of x, it says it's sine of pi over 2, cosine of pi over 4, not cosine of x or g or whatever. Take a look at that carefully and think to yourself, am I taking a derivative of a function or am I taking a derivative of an evaluation? And evaluations always end up as numbers, right? Because we're evaluating it at some number. So what would be the actual derivative of this as a result? Okay, so I think everything else should be pretty easy to do. Again, I think I wrote this out so you guys have a bit more practice with natural log, EDX, cosine functions, especially like number 6. Okay, again, this is just not big, but this is just a giant, what do you call it? Chain rule function, okay? For what values of k does the graph of g of x equals k e to 2x plus 3x have a normal line whose slope is negative 1/5 when x equals to 1? Well, that's very, a lot of information there. So again, I would have to take the derivative of this function, and when I find this, I'm going to find the slope of this function, but it's going to be in terms of k. But remember that if the normal line whose slope is negative 1/5, what is the tangent line slope? I have to do what? Flip it back upside down and then get rid of the negative sign. So you really find out your tangent slope is 5, and I'm going to equal it to what? To the tangent line function that I have. I have to take the derivative at x equal to 1, and I'll figure out what k is. Maybe that helps you out, maybe not, I don't know. But okay, So it's 11:56. Are there any other questions or closing remarks? For those of you who missed it, like Jared, you just came in right now, I'm going to put a video of this up on the like the updates page or materials page. Maybe I'll put and you can kind of watch what we did today. You should work a bit of 6 out. Or work a bit of 6. Okay, work a bit of 6. All right, here's a bit of 6. Here's a bit right there for you. I'm just messing with you. Oh, you want to see the chain rule? Yes. Okay. All right. So 5 cosine squared of pi minus x. Okay, so I'm going to go ahead and work just a little bit of this out. Now, there's 2 things you can do. Well, actually just 1 thing. So remember that this thing is squared, right? So I take the derivative of this, I take the derivative of cosine squared first, okay? So remember that this 2 is going to come down, right? And then I'm going to take the derivative of this guy, so it should be sine, right? Negative sine. But remember, you leave the inside alone, okay? Then I'm going to take a derivative of what? Times the inside now. So what's the derivative of pi minus 6 going to be? Pi minus x, what am I saying? Pi minus x, what's the derivative of this going to be?
Would just be -1.
Very good, -1. Okay, so that's as far as I'm going to go. What I want you to do is this. If you have a little bit of trouble, I need to put this up here too. Go to something online called the derivative calculator. I'm going to go ahead and type this out real quick. Okay, derivative calculator. Clear my drawing real quick. All right, guys, I'm putting this into the chat. Derivativecalculator.net. So I'm going to go ahead and share this one more time. So here's your thing. Here's your function, right? It was 5 cosine of pi. So in this case, you can't do a pi. You got to do pi like this. You got to type in pi. Do you see that? Then minus x, and then the whole thing is raised to the 2nd power. Okay, so do you see how I wrote it? But this is how it's going to recognize it. Now, okay, so you have to write the square on the outside. Take a derivative of this function. Now you double check your work. Okay. So let me show the steps. Here's the steps. See? Okay, so I made a little mistake here. I thought so. See how I can double check my work now? The 2 came down, right? Okay, the 2 came down, but nothing happened to the cosine of that function yet. Okay? I don't know why it changed to that. My input is not that, dude. I don't know why. But anyway, this part is correct. So then the next part was, then take a derivative of cosine of x. So this becomes a chain of a chain of a chain, because the only part that they left out here for some reason was the x minus pi minus x, which I don't understand why. So my input has been rewritten and simplified. That's all I did. And I think it's been rewritten and simplified because I could actually take this out and do what's cosine of pi minus x. They actually used a trig identity Remember that cosine of A plus A minus B, where does that actually expand to? So that's why. So I actually end up with this. So if I take a look at cosine of A minus B, identity, remember that the cosine of A minus B is this. Cosine A, cosine B, plus sine A, plus sine B. Okay, and that's what they have here. So looking at the derivative calculator, this is what they end up with. Okay. So in the situation here, the 2 comes down, but remember the base is not affected. And then times the derivative of its base, which is cosine of x, becomes negative sine of x. And then like what Sarah said, since it was pi minus x and I kept that there, I take the derivative that one more time and I get what? -1 coming out. So notice there's a negative sign out here now. So that's what happens there. So that's hopefully a very helpful tool. I'll actually, in this moment, put this in here. And there you go. Okay. Hopefully you guys can see that. Good. All right. Okay, so it is 12:04. I'm gonna go ahead and stop for today. I hope that helped. I hope that helps you guys out, and you guys have a good Thanksgiving break. You guys can kind of like just get rid of this homework right away, and then like have it already like turned in if you want to. Okay. So I'm glad I helped you guys out. Again, those of you who are here right now, I believe Jared was here for a moment, but he left. If you're here right now, like I said, I'm going to go ahead and finish this recording, and I'll upload this on the updates page for the moment. And then I'll try to create like a video tab on the top. You know how the announcements. So I'm going to try to do like another video tab up there. And that way you can click on the little Thanksgiving break session that we had. Okay. All right, guys. Enjoy your week. If you have any questions, feel free to shoot me a message. I'll always try to answer you guys real quick and straight to the point. Okay. All right.